on the Kelvin-Helmholtz instability and BNS mergers. This is a work that I've done with my collaborators, Sam, who was here earlier, Elias Moss, who just gave a talk, and my supervisor, Luciano Rizzola. Okay, I will start with a rather basic introduction, maybe what maybe magnetic fields at isolated neutron stars look like. And I think there's really not that much known evidently from observations about them. Traditionally, the dipole model was invoked in order to model the magnetosphere of isolated neutron stars. But as we've seen today, also in a dynamical context, with two neutron stars, this can be highly variable. However, also for isolated neutron stars, as recent DICE observations, for instance, have shown, the magnetic field topology of isolated stars can be quite different and also include higher order multipoles. For instance, here on the right-hand side, you can see an isolated neutron star observed by NICER, where the hotspots are essentially modeled. These hotspots come from plasma, which is accreted on the neutron stars and following magnetic field lines. And due to the frozen flux conditions, essentially this tells one something about the magnetic field topology of the magnetosphere, as can be seen in the lower right panel, for instance, in an ideal MHD simulation. Well, apart from that, of course, also as many people in this conference already have been shown, magnetic fields are quite important for a lot of different observational phenomena from BNS mergers. And just one of these is the observation of a gamma ray burst, which was seen 1.7 seconds after the GW17 or 817, so after the gravitational wave signal that we have observed in 2017. And it also is linked, of course, to the intricate details that binary neutron stars can follow after the merger, where as a simplistic view is presented in the lower panel, where you can essentially see how two lower mass neutron stars, so ones that form a supermassive neutron star that's maybe not expected to collapse when differential rotation is removed, form the supermassive neutron star, and then will evolve on the order of seconds, or 10 to the 4 seconds, and eventually form a black hole or a stable neutron star. Okay. Again, as we have seen today and also in the previous days, there was a lot of recent work on magnetic polar outflows that can be generated in binary neutron star mergers. And essentially, this has to do with a concentration of a lot of magnetic energy and magnetic pressure in the polar regions, which can then power magnetic tower outflows, as we have seen today. These can be on the order of 10 to the 51 to 10 to the 53 ergs per second, which might be necessary in order to explain observations of short gamma ray bursts. But also they can, I think, power not only ultra-relativistic outflows, but also multi-relativistic outflows, which actually could contribute to the kilonova signal and lead to short-term blue kilonovae. Okay, and now I will move on to actually a process which can amplify a magnetic field strongly in binary neutron star mergers, and this is turbulence. We have also heard a lot about the subgrid-scale modeling from Carlos Valenzuela and why this is important in order to reach actually the magnetic fields necessary to explain, I think, all of these observations that I've just tried to mention briefly in the previous few slides, which highly depend on really strong magnetic fields which are active in the post-merger phase. And here on a couple of pictures, I want to briefly and intuitively explain how this is working. So essentially, when the two neutron stars start to approach each other, they will be subject to strong tidal forces, which will essentially lead to this two teardrop-shaped neutron stars, which will rub against each other and generate this very strong shear layer between the two neutron stars. This shear layer will be subject to the Kelvin-Helmholtz instability, which eventually will generate these eddies that you can see over there. So matter will be essentially swirling in, creating these large-scale eddies, and eventually turbulence might or might not develop in the whole region of the two stars, where after some time, in the middle picture, for instance, which is similar at around 5 to 10 milliseconds post-merger, you will have a fully turbulent setup in the hypermassive or supermassive neutron star remnant. And in color coding, in these two plots, you essentially see the magnetic field strength. And the reason is that due to the ideal MHD approximation, essentially the magnetic flux is frozen into the fluid, such that always when you start creating these eddies and matter is essentially swirling in, magnetic fields get strongly sheared and due to this process amplified. So essentially the local small-scale kinetic energy due to the small-scale dynamo effect will amplify magnetic fields and transfer small-scale kinetic energy to small-scale magnetic energy. And further evidence for this process was provided by Aguilera Mire in 2020, where you essentially see the spectrum, I think, of the magnetic and the kinetic energy on the right-hand side. So in solid lines, I'm showing the kinetic energy spectrum, and in dashed lines, you can see the magnetic energy spectrum. And as you would see, and essentially the two, let's say, the two lines above, both of these spectra denote what would you expect from turbulent theory. So this is the Kolmogorov slope for the kinetic energy and the Kazantsev slope for the magnetic energy. And as you would intuitively expect from this type of small-scale dynamo, magnetic fields will get amplified on the smallest scales, the strongest, as the Kelvin-Helmholtz instability is sensitive to the wavelength of the perturbation, where the smallest scales grow the fastest, such that also the amplification is the strongest in the smallest scales. And you get this sort of, if you compare the magnetic energy spectrum to the kinetic one, you see an inverse slope. And this is intuitive because you would expect a strong amplification at the smallest scales. Moving on, I'm showing some pictures that we've seen yesterday already. This process will eventually saturate at some point, and this is when magnetic energy cannot be transferred any longer. Kinetic energy cannot be transferred any longer into the magnetic sector. So this is essentially a point where magnetic fields on a certain scale are strong enough to backreact to the fluid and to counteract this eddy-type motion that is actually dragging magnetic field lines into rotation and amplifying them in this way. And the plot that Carlos Valenzuela has shown already yesterday is that they were able to achieve a saturated state at an average of 10 to the 16 Gauss in the highest density region of the binary neutron star merger by using high resolution simulations, medium resolution simulations with LES, and also high resolution simulations with LES. So essentially, I'm referring only to the, on the left-hand side, the top panel, I'm referring to the three curves which are the highest. And as you can see, even though you include LES terms, the average magnetic field strength does not really change a lot, which means that you are at the level where the magnetic field lines are, where the magnetic field strength is backreacting, and you saturate this amplification process happening due to the Kelvin-Helmholtz instability. Then also, as mentioned yesterday, the group was also exploring different initial magnetic field topologies, which might, well, the hypothesis is that whether initial magnetic field topologies can or cannot lead to different outcomes in this initial magnetic field amplification phase. And they were exploring a couple of different initial conditions, for instance, a standard dipolar field that people usually assume, then a strong dipolar field in order to somehow include this amplification that is expected to proceed during the Kelvin-Helmholtz instability stage and to reach this saturation, let's say, somewhat artificially, but also a misaligned dipole, also somehow higher order multipoles. And essentially what was shown is that here in the middle panel, you see that all of these topologies do not really matter as turbulence becomes isotropic. The initial magnetic field topology is washed away, and you reach a turbulent isotropic state, which is similar or the same for all the different configurations. However, it's interesting that many groups who actually model neutron stars on longer timescales, so not on milliseconds, but maybe on a timescale of 10,000s or 100,000s of years after their birth in a supernova, they are considering mainly magnetic fields which are confined to the crust in order to study their magnetic evolution, their rotational evolution, also cooling curves from newborn neutron stars. And and one, let's say, microphysical assumption for this, or microphysical motivation for this type of setup, is that At some point, the core cools down and protons become superconducting. And if the core is really a type 1 superconducting core, magnetic field lines in the core might be expelled on very short timescales compared to the dynamical compared to the evolution timescale of the single neutron star, such that eventually the core becomes unmagnetized. And we were thinking, okay, whether this actually might have an observable imprint or an effect on this initial Kelvin-Helmholtz instability-driven stage in binary neutron star mergers. So essentially, that's just another initial topology that we wanted to explore and see whether this makes an impact, given the importance of magnetic fields and even specifically strong magnetic fields in the post-merger phase. So just a few remarks about the methods that we use. So first of all, on the lower panels, you can see our initial conditions. So it's very simple. We just compare a full setup where the magnetic fields are just dipolar everywhere in the neutron star, as typically done, compared to dipolar field lines, which are seated only in the crust of the magnetic field. Yes. So this is a snapshot roughly one millisecond before merger. And for these simulations, we use the Einstein Toolkit infrastructure. We use the Frankfurt, Illinois GMHD code with fourth order methods developed by Most and collaborators in Frankfurt. And it has a vector potential based constraint transport and finite temperature equations of state. For these simulations, we do not use neutrinos. However, it might be, I don't really think that they might be that important, but maybe for a longer term evolution, if one wants to study the outcome of our simulations and also related to the development of these polar magnetic outflows, they might be important. Of course, we need to have quite high resolutions in order this Kelvin-Helmholtz instability stage. Otherwise, you don't really get enough resolution and a small enough shear layer in order to have significant growth in the Kelvin-Helmholtz stage. And just to emphasize really in ideal MHD, the main processes that are important to amplify the magnetic field or to transfer essentially kinetic energy to magnetic energy, the relativistic ideal MHD equations can be rewritten in this very simple form that I'm showing here on the upper left, where you essentially just have an advection equation for the magnetic energy with some source terms on the right. And you see that there are essentially just two hydrodynamic processes that can transfer the energy from one sector to another in ideal MHD, and this is essentially expansion and compression of the fluid, where flux is conserved, and if you expand, the magnetic field is doing work on the fluid such that it is decreasing. Or you have the shearing term on the which is the second term on the right hand side of the magnetic source term. There should be a plus. Sorry. So that's essentially a shearing term where the shear tensor of the fluid is coupling to the magnetic fields, such that this is essentially what is acting, for instance, in magnetic winding, or also in the Kelvin-Helmholtz instability, where magnetic fields are strongly sheared by the eddy-type flow, eddy-type hydrodynamic flow due to the Kelvin-Helmholtz instability. And now let's jump into a few of the results that we have shown that we got. So there's a lot of things here to talk about, but I want you maybe to start focusing just on the left panel and on the solid lines, which are the high resolution simulations for the full configuration and the cross configuration that we have simulated. And what you can see at the end of these curves, so at roughly 16 milliseconds, is that the two energies differ by roughly 1 order of magnitude, which we found quite significant. And trying to understand where this comes from, we have identified different stages which are active during the evolution, from the merger of the two neutron stars to the end of our simulations. And for the most part, the stages are very essentially the same for the full configuration and the cross configuration. The real difference, in order to get this 1 order of magnitude difference between the two configurations, is essentially in the Kelvin-Helmholtz driven instability stage, which is just the most left stage. We try to use different shadings in this plot to highlight the different stages, and we see that in the full configuration, this initial amplification phase is significantly prolonged compared to the cross configuration. That's why we see that for some reason in the cross configuration, the initial amplification due to the Kelvin-Helmholtz instability just dies off earlier and can't reach the same energies as will be reached by the full configuration. Afterwards, the stages are somewhat similar, and at some point, magnetic winding kicks in, which is then letting the magnetic energy grow on a timescale expected to be proportional to t squared. And what I will try to understand in the next slides is that, okay, how is this happening? Why is the cross configuration having an earlier end of magnetic field amplification than the full configuration? But on the right plot, for instance, it's also interesting to analyze the growth rate of the magnetic energy during this Kelvin-Helmholtz amplification phase. And what we see are initially, let's say, very early on in the amplification, peaks in the growth rate, which are comparable for both simulations. And this is essentially as expected, as one would expect, as the growth rate is simply dominated by the smallest wavelengths that are unstable in the Kelvin-Helmholtz instability, such that and these smallest scales just depend on resolution, such that if we use the same resolution which we do for both cases, we would expect an initial comparable growth rate. Afterwards, we see a quasi-periodic peaks occurring in both configurations, even though the cross configuration is dying out earlier. And it's very nice that these peaks are correlated essentially with the appearance of shear layers when the two neutron stars are bouncing against each other. So always when there is a shear layer appearing between the two bouncing cores of the neutron stars, the Kelvin-Helmholtz instability can get active, even though maybe with a smaller growth rate, because the shear layer is essentially extending between the two cores due to turbulence. And magnetic energy can get amplified until the shear layer is not significant enough anymore in order to amplify the field. So what's the reason why the cross configuration is essentially not able to, or at least in our simulations, not able to have such a strong magnetic field amplification? And the main reason for this is that quite early in the post-merger phase, roughly at the first bounce of the two neutron star cores, there's a lot of material which is getting ejected at the crust or at the surface of the two neutron stars. And I'm trying to show this in these two plots over here, where you can see, for instance, that there are strongly magnetized islands at the outer boundaries of the newly forming hypermassive neutron stars. And just shortly after the snapshot, it's exactly these low density regions where most of the magnetic energy is concentrated for the crust case, which get ejected violently just due to dynamical ejector. And also turbulence is starting to get active in these regions, even though the turbulence is not due to the Kelvin-Helmholtz instability. It will further increase the ejection of matter and essentially remove important magnetized material, which could otherwise be used in the shear layer interior to the stars or closer to the stars in order to amplify the energy. So the main process that we identify for this early stop of the amplification process is that important magnetized material at the crust of the crust configuration it's not ejected fully from the domain, but it's removed from the important regions of the hypermassive neutron star, where it essentially can act as a fuel to amplify the magnetic field further. And of course, for the full configuration, this is not happening because there's just magnetic fuel available everywhere in the star, and such that the shear layers which are generated by the merger process always have some fuel to amplify the magnetic field. Okay. We've also then looked at gravitational waves from these two objects. And we have found a difference there, which we also link to the increasing magnetic field strength in the full configuration versus the cross configuration. So here, I'm just showing the gravitational wave signal in the L equals to M equals to bar mode. And the main difference that we see between these two configurations is that the full configuration has a stronger decay in the gravitational wave signal than the cross configuration does. And we link this to an earlier development of axis symmetry in the hypermassive neutron star after merger, due to stronger magnetic fields that can be developed. So essentially, what we see in the simulations is that the the neutron star that is developed has a more axisymmetric profile, which is shown here in the cartoon for simplicity. Okay, and now I wanted to show the movie, again illustrating the different stages that I've just talked about. Here. Can the movie also be seen from the online audience? That's good. Yeah. Okay. Okay, so what we see here are slices of the magnetic field strength in the equatorial plane. On the two above panels, on the left you have the full configuration, on the right you have the cross configuration, and below you have the the same magnetic field strength, but in the XZ plane. And as the two neutron stars start to approach, you see the development of the Kelvin-Helmholtz instability just at the shear layer between the two stars, which is very sensitive to resolution. And you immediately see that the magnetic field strength is getting amplified quite strongly. As the two stars then move further, roughly at this stage was the snapshot where I tried to show you the magnetic islands located at the outer parts of the two neutron stars. So for instance, here, these islands, which actually compared to the full configuration, make up a higher percentage of the total magnetic energy, simply because of the topology of the two magnetic fields. This is now the first bounce. So this is the first collision, and now the neutron stars will bounce back. And in this bouncing, you see that there's a lot of crustal material and low density material, which is removed from the, let's say, from the denser portions or the portions of the neutron stars where shear layers can develop, and magnetic energy is essentially located in the outer layers. Of course, it then cannot participate anymore in the Kelvin-Helmholtz shear layers, which can amplify the magnetic field, which is not the case in the full configuration. Yeah, and then the two neutron stars are getting more turbulent, even though we see that turbulence does not really, in our simulations, penetrate to the interior or the core of the two neutron stars, even though everything outside looks like a big mess. And at some point, you see that there's, in both configurations, a ring development, a strong magnetized ring, which I think also other groups have observed, which is essentially at the location where the rotational profile of the hypermassive neutron star has the highest gradient. So this is a winding effect, which strongly amplifies the magnetic field there. Okay.
Could you sorry, there was like a sudden change in field geometry at around third into the movie. Would you mind replaying it?
Yeah, sure.
And before that, the breaking up suddenly appears on the left.
Sorry, what are the density contours that you have tuned there, right?
Yeah, the outer density contour is at 10 to the 13 gram per cubic centimeter, and the inner one is at 7 times 10 to the 14. Okay.
Thank you.
Yeah. We have also carried out low resolution simulations in order to see whether this trend that, or whether the observation that we have, so whether the difference that we have is sensitive to resolution, or whether we observe a trend which is consistent with our interpretation, or whether it's just a resolution effect. And what we essentially see is that also the low resolution simulations, where's full screen? Yeah. What we essentially see is also that the low resolution simulations show essentially a very similar behavior, even though for them the Kelvin-Helmholtz instability stage is somewhat prolonged. And we link this to due to the lower resolution, we also have a worse we have a worse resolution in the crust, which would actually be very, very fine. And due to the low resolution, it is extended over a larger amount of grid points, such that also the magnetic fields located in the crust essentially after some time, have a bigger extent. And due to this fact, magnetic fields can somehow amplify longer in the whole amplification process. However, the overall trend, so the overall difference that we observe between crust and full, somehow remains the same. Okay. Let me also briefly comment on a recent work that was that I think came out recently by Aguilera Mires, so essentially by Carlos Palenzuela's groups, where they used subgrid scale modeling in order to investigate essentially the same scenario. And I want just to briefly comment on that what they see for a, let's say, similar setup where the resolution is comparable, but with subgrid scale terms, is that they do not observe this trend that I've just mentioned. So the main difference can be seen, for instance, on the lower right panel in the energies, where at some point the dotted lines show the magnetic energy, and the blue line is the full configuration, and the black line is the cross configuration. And at some point, roughly here it's at 7 milliseconds, the cross configuration catches up with the full configuration. And if you look a little bit into the simulation and compare the simulation roughly at equal time snapshots, what you see, I think roughly, is that, first of all, the density contours, they are comparable. The outer contour should be at the same density, while the inner contour of Aguilera Mires' work should be somewhat extended at a lower density compared to ours. However, I think one main difference that can be appreciated is it seems that these simulations seem to show a stronger mixing and a stronger development of turbulence in the denser parts of the neutron stars for a comparable simulation. So this might be a reason why actually the cross configuration is able to catch up with the full configuration. However, there are also some other differences between our simulations, which actually might indicate interesting physics that can be linked to this amplification process. So they're using a different equation of state. And as mentioned already, SGS modeling, so subgrid scale modeling that Carlos was talking about yesterday. And it would be interesting to, I think, to find out where this difference comes from and whether this is actually something linked to resolution, as indicated by the inclusion of SGS terms, or maybe it's linked to actual physics related to the equation of state, which might generate more shear layers, or which might lead to more bounces, therefore more shear layers, and shear layers which survive for a longer time, and therefore to more amplification, or its resolution effect. So this is just a brief summary. How much time do I have left?
We have 9 minutes.
Okay, so this is just a brief summary of what I've talked about. So crustal fields in our simulation seem to disfavor strong magnetic energies in the post-merger phase, and that might be actually important for all these polar outflows that have been observed recently in recent papers. However, I think there's an open question about really the impact of extreme resolution. So we used 70 meters. Maybe we really need to go down to, I don't know, maybe 30 meters in order to have a conclusive answer for this. But also it might relate to other binary parameters like total mass of the binary or the equation of state. And maybe I want to say, since Elias made a very nice connection of binary neutron stars and microphysics, especially to bulk viscosity, I might use the last few minutes actually to talk about some recent work of mine and my collaborators on bulk viscosity, just as a brief motivation, even though Elias has talked about this quite extensively. Bulk viscosity neutron star measures essentially can appear due to off-equilibrium effects in chemical equilibration. And an easy way to understand this is to look at a piston which consists of different particle species, which can transform into one and another. And there are different timescales, and the piston is subject to a periodic perturbation. And if there are different timescales compared to the perturbation times, where you have to compare the perturbation timescale against the reaction timescale, when the particles in this piston can transform to one another. And assuming that the perturbation timescale is now much, much shorter than the reaction timescale, you get on the lower plot here in the left panel, you get a system which essentially does not change its composition. The particles simply do not have enough time to transform into one another. So you have particle A, particle B, but in a time scale of one perturbation cycle, they just don't realize that they actually need to transform. They don't have enough time to react. And on the opposite, there's a case where the perturbation timescale is much longer than the reaction timescale, such that the particles are always reaching chemical equilibrium. And essentially, during one very slow cycle of the perturbation, at each instance where the thermodynamic conditions, so density and temperature are changing, the particles immediately react, create a new equilibrium, and so equilibrium is always established. But bulk viscosity actually is quite interesting because it exactly appears when the time scale of the perturbation is similar to the time scale of the reactions of the particles, which means that during one perturbation cycle, the particles at the same time are non-reversibly reacting with one another, such that such an entropy can be created. And in this phase diagram of volume and composition, after one cycle, you do not really get back to the same point as you have been before. And this means that some dissipation is happening, and some of the compressional energy is actually dissipated and transformed into heat. From this concept, I think there's been a lot of work, specifically by Michail. This resonant bulk viscosity form can be worked out, where you can see that it explicitly depends on omega, the perturbation timescale, that's the movement of the piston, and on lambda, which is the reaction timescale of the reactions of the chemical particles. And we have done a very simple and crude approximation where we said, okay, let's implement bulk viscosity in Barry-Newton star mergers, but let's take it as a constant, as an upper limit for the maximum effect that could be observed, where our values are motivated from values that Elias has presented, I think, in his slides today, where we have used a high viscosity of 10 to the 30, which is probably very high, and a more realistic case might be the low viscosity that we used in these simulations, which is around 2 times 10 to the 29 grams per cubic centimeter. And what we essentially see is, as expected, bulk viscosity starts to damp the density oscillations of the two neutron star cores, and therefore is reducing the gravitational wave emission of the merger. However, of course, this is highly linked to the magnitude of the bulk viscosity that we put in. And as you can see, maybe the difference between the zero viscosity case and the low viscosity case is quite small, such that maybe for realistic bulk viscosities, we do not really observe a big difference. We have then also calculated other quantities, for instance, the spectrum of gravitational wave emission, where we see a difference in the F2 peak. So that's the frequency of the L equals to M equals to mode of the bar mode of the two neutron stars, where we see with higher viscosity, essentially, this frequency gets higher because the whole object gets more compact and can't really transfer, can't really lose a lot of rotational energy to outer layers and also to gravitational wave emission. That's why we also observe on the right-hand side that the gravitational wave emission is reduced in the viscous cases. Even though, again, I want to emphasize, maybe for the more realistic case of low viscosity, so the difference between the green and the black line is just 1% in gravitational wave emission. And yeah, thank you very much for your attention. I think I will leave this slide open.
We have some time, a couple minutes for questions. Anyone have any?
Should I go there?
Yeah, why don't you come up so that people online can hear?
Yeah, so very nice talk. I was wondering, maybe this is a very naive question. I don't know. So we are we're sure that the isolated pulsars that we see, the magnetic fields are of the order of 10 to the 8 to 10 to the 11 if they are not magnetars. But that's the surface magnetic field, right? I'm wondering, do you have strong fields inside in the core of the star with the orders of 10 to the 14 or 15 that are inside, and then if they are the star it goes in a merger, then this is what the seed that you use to amplify it even further. So the question is, do we have any clue of what's going on with the magnetic field inside the star?
So to my understanding is that I think so I'm not an expert on this. I think strong magnetic fields inside the star should be generated due to the supernova collapse. And if the progenitor stars already had magnetic fields just due to the collapse, also these should be conserved in the interior. Mm-hmm. And to my understanding is that I think the timescales on which the core magnetic fields develop or evolve are very uncertain. So I've seen a couple of papers and not that many. So maybe also somebody knows more than me, but the timescales on which these core magnetic fields evolve can change by orders of magnitude. So there are also people that claim that core magnetic fields will persist, I think, for a long time scale, will not be removed from the core. And, right. So, and then, of course, depending on the mechanism which is acting in the Kelvin-Helmholtz instability stage. So specifically, whether core magnetic fields are able to mix efficiently and amplify the field, then of course, if you have very strong fields initially that are preserved from collapse to merger, then they will also add to the amplification. However, if the turbulent mixing, if I don't know, you do a meter simulation of 12 meters like Yuchi, and you see that somehow the material in the core is not really getting mixed up that strongly, and all the mixing and all the amplification is happening more in the outer layers, then maybe they will not matter that much in the overall amplification.
I see. So basically that's doing the inverse problem that you're doing here, right? Like instead of putting something in the cross, you put nothing and just something in the, okay.
So yeah.
I see.
Thank you.